Hello everyone, it's been a long time since I last saw you, and today is Christmas Day. So, to give you all a Christmas present, now of course Santa Claus won't be at your door delivering presents, but thankfully I'm here. And so today I'm going to present to you a plethora of formulas for my favorite constant, the natural logarithm of 2. For those who don't know, it is the constant which if you take e to the power on this number, where e equals to about 2.71828, it is 2. The result will be 2, that is. Now, ln 2, as it's colloquially called, is approximately equal to 0.6931471855. I just gave you the first 11 decimal places, which should be almost perfect for every purpose you might dream of. Now, how do we find formulas for a constant? Now, sure, you might know the quadratic formula, you might know the formula for the area of a circle, but how do we find formulas for a constant? A constant is just a constant, right? Wrong. How do we find formulas? Well, usually when we make a function to output a constant, it must output this constant when we feed it something simple like 1 or half or 2 even. That's how the alternating odd number series for pi was first created. 4 times 1 over 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus, and it goes on to infinity. So there are 3 methods we can use. We can use Maclaurin or Taylor series, which you might be familiar with if you took calculus. We might sum 2 terms at a time to form new series, though they are practically mathematically equivalent. And we might use the addition formulae for logarithms, tan inverse x, and hyperbolic tangent inverse x. Now, there are a few other methods which I'm going to discuss later, which are not in this list, which may include Riemann sums, trapezoidal rule, and Simpson's rule. Now, here's a disclaimer. If you don't understand anything, I'm definitely going to explain it in this video. Alright? Now, let's move on to the actual formula creating. Now, the first method is to use Maclaurin series. So the Maclaurin series for ln 1 plus x is found in the FF19 dialogue booklet if you took Cambridge A-level or A-level mathematics. Then you get ln 1 plus x equals to this. Now there are 2 options. You have ln 2 is ln 1 plus 1 or negative ln 1 plus negative half. Now the second expression, the second logarithmic expression may seem a little going around in circles, but you realize it's actually negative ln half, which equals to ln 2, and you follow the reciprocal formula for logarithms. Now, if we take x equals to 1, we will get the well-known alternating harmonic series. The reciprocals on the terms grow linearly, 1, 2, 3, 4, and around 1 decimal digit per 10 to the power of n terms. Admittedly, this is not very efficient when you want to find ln 2 on computational purposes, such as I can't think of any other purpose for ln 2 except for radioactive decay. So, admittedly, if you want to use this, well, it's sorry, but there are better formulas in store. Now, when you use x equals to negative half, you get a much faster formula. This is definitely faster because the reciprocals on terms grow times to O n e to the power of n, or roughly exponentially. So it's around 1 decimal digit per log 210 is 3.32 terms. Now of course, if n grows bigger, then more decimal digits will be created per term. And this is admittedly more efficient than using the alternate harmonic series. Now, we can also use the Maclaurin series for the hyperbolic tangent. Now, you see, the hyperbolic tangent inverse I meant. So ln 2 could be tangent hyperbolic inverse 3 over 5, which it's not very simple. But you can use twice the hyperbolic tangent on 1 over 3, which is more complicated and simple at the same time in that it uses 2 terms, but each term is a reciprocal of some whole number, and you can just multiply it by 2. Now, as you can see here, ln 2 is 2 tangent hyperbolic inverse 1 over 3, and then you substitute it into the Maclaurin series and you get this. Now, the next 3 steps you see are the conversions on this to what is called a Bailey-Bauerlein-Plouffe type formula, where the base here is 9. And then, so a Bailey-Bauerlein type formula is usually a constant times 1 over a to the power of n, where a is some number, and then some linear combination of fractions which don't have anything to do with a. Now, so far we have these 3 formulae of 4. If you want to count the 2 separate formulae or the tangent hyperbolic series as the different formulae. Now, let us go to another method. Well, you say these formulas are not fast enough. Well, definitely, they aren't. Method 2, sum two or more terms of a series. Now this is where the BBP representations come in. So the formulas being all show bases 2 and 9. So you go back, you see n times 2 to the power of n and 6 over 2n minus 1 times 9 to the power of n. So we can create analogous formulae for bases 2 to the power of n and 9 to the power of n. So as you can see here, this is summing two terms at a time to produce a formula of base 4 to the power of n. Now, and you come to realize something for base 4 actually. So you come to realize that this is not actually a different series. This is the same series all along. And you can create another series for base 8 to the power of 8. And then 8 to the power of n is the term, is the exponential term we are discussing. Now, as you can see here, we can create an analogous formula for all bases 2 to the power of n, where n is some integer. And of course, the holy grail on this is obviously a generalization. That's why the bottom formula is a generalization of all the formulae up top. Now, we can create an analogous formula of base 81 and base 9 to the power of n. Now, look, you see, these aren't actually mathematically different series. Now, you say these series are not fast enough. Well, they aren't. Now, let's look at another term which is definitely going to produce slower series. Now, this may be counterproductive to what you want, but this is an interesting diversion. Now, let's talk about methods of integration. Let's talk about Riemann sums. Now, how is this supposed to help? You see this integral here, the integral of 1 over x from a to 2a is ln 2. And you can see an approximation of Riemann sums where a is equal to 10. The thinner the rectangles, the smaller the discrepancy. And for this video, we are always going to use with 1. Now, as you can see, summing all the fractions will give you this. So you have 1 over 10, let's say 1 over 10, 1 over 11, 1 over 12, 1 over 13, 1 over 14, and then so on. Now, as you can see here, we are going to add 2 more rectangles here on the right and remove that rectangle on the left. That way, we always add the term 1 over 2n plus 1 over 2n plus 1 minus 1 over n to get this. And yes, if you're wondering, I like my fractions split because they can help you understand what the formula is actually made out of. That's why I like partial fractions. Moving on, let us discuss the trapezoidal rule. It's an approximation of a curve using line segments. Now, this is actually getting really complicated, so you don't understand, don't fret. Now, as you can see here, segment, and you have one segment. Now, this is very obviously twice the sum. So as you see here, 1 is 1 over 1 and 1 over 2. That's why I've written numbered segments. When we have 2 segments, we have 1 over 2, 2 over 3, and 1 over 4. Now, how is this supposed to help? So on the left, we are subtracting 1 over n plus 1 and 1 over n plus 2. On the right, we're adding 1 over 2n plus 2, 2 over 2n plus 3, and 1 over 2n plus 4. This pattern breaks where we are trying to break from 1 to 2 segments. That's why I started with 2 segments and having n plus 2 as our, say, n index. So that's why I picked 2 segments as our n is equal to 0. And here is the simplification of the formula. From ln 2 is equal to this mess of fractions and then much simplified, although I still prefer my fractions split. Now, let's talk about another rule, Simpson's rule. It's an approximation of a curve using fragments of parabolae for all parabolas, and it only works for an even number of segments. Now, as you can see here, and you have 4 segments, it's perfectly fine, but if you go from 2 to 4 segments, it makes the formula. And then you have this utter mess of fractions at the bottom. And then I helped you simplify the entire barrage of fractions to a more manageable barrage of fractions. Now, as you can see here, you might see Pascal's triangle in here. So you take the third fraction and then you express it as 6 over 4n plus 6. Then you get Pascal's triangle. So far, you have these 2 formulas. But what about this? Suppose you want analogous formulas for where the n is 1 and 3. Now, this is what I call a careless generalization. Thinking about an idea and then testing it using some computer algebra system. Here I use Wolfram Alpha and I proofread all the formulas using Wolfram Alpha again. So as you can see here, these are the formulae that it generated. And as you can see, they get more complicated when you go down. However, they admittedly become simpler when you get to even terms. So, you might also realize this. There are no analogous formulae like this for n, where the n The linear term is 5n plus something or 6n plus something or anything above. Now, that's it. That's all I'm gonna do. So, you say, not fast enough? Well, technically you're right. So, we're going to learn how to convert logarithms into even smaller logarithms. So, the problem of finding a set of formulae for ln 2 then reduced to finding a set of super particular ratios that multiply to 2. Sturmer's theorem gives a finite bound of number of consecutive pairs of smooth numbers. Now, smooth numbers are numbers which use only a set of primes up to some number n. So, our set of primes you can use can be 2, or 2 and 3, or 2, 3 and 5, or 2, 3, 5 and 7. Now, let's call this the tree-limit decomposition. Tree-limit is a term currently used in music theory, but here I'm gonna use this to apply to smooth numbers, or I'm gonna call them three-limit numbers if you will. Now, as you can see here, the top one is a decomposition of 2 into two three-limit fractions. So ln 2, you will get this formula, and in case you're wondering, the sigma applies to all the terms that come after it. So ln 2 could also be 1 over n times 4 to the power of n plus 1 over n times 5 to the power of n plus 1 over n times 6 to the power of n due to its composition of 2 into 3 super particular fractions. And then of course we can continue this series indefinitely, and this can be thought of as a refinement of the Riemann sum method. So 2 could be factorized into this, and 3 over 2 could be factorized into another pair of tree-limit ratios. So 2 is 4 over 3 squared times 9 over 8. And of course, we can convert this to another formula for the natural logarithm of 2. Now, here is the very lengthy decomposition of 2 into 5 limit ratios. And I bet you can see all the steps that can unfold like a Christmas tree. Sadly, I wish this slide was portrait. That way you could see the whole decomposition. Now, here is the analogous decomposition for 7 limit ratios. Now, the decision tree for this is actually very, very large, and it will be too large to put on a slide, in fact. That's why I crystallized the entire formula into this. Now, you see, not fast enough? And you're technically right, because we can convert logarithms like this to hyperbolic tangents. So, we realized that a number a could be taken, the logarithm for summation formula could be converted into a hyperbolic tangent summation formula, and then it increases the base of the exponential term as well. How cool is that? Now, here are the formulae we encountered earlier, as well as their hyperbolic tangent equivalents. So as you can see here, there's like a mirror between the logarithmic and hyperbolic tangent formulae, except that the hyperbolic tangent formulae converge to the actual value much faster. So when you go check out even the first term of the bottom right formula, you'll find that it converts ln 2 in 4 decimal places, which is quite wondrous for one term. So I suggest we all give you a challenge. Let me give you a chance to submit your formulae for the natural logarithm of 2 in the comments if you have one. And you have a method to generate an infinite series of formulae, even better. And also, you can show me your proof and methods. The winner of this challenge will receive a special prize from me. I won't tell you what this special prize is because 1, I haven't decided it yet, and 2, I wouldn't expect there might be a mathematical genius watching this video and finding another formula for natural logarithm 2, which is way better than my formula. And it's fine, you know. It's cool when you learn from other people. Alright, this video is approaching 14 minutes in length, and it's quite long for one of my videos. So, thank you and have a Merry Christmas and a Happy New Year. And here's my Christmas present to you. Goodbye!